lecture on a technique I use specifically in my research, and I want to talk about this as a complement to Umut's lecture. Umut gave you a specific way of constructing gauge theories within the context of string theory, and I'm going to talk about a different one. And this has some advantages versus this view description, like the orographic description. And one of the major advantages is that you don't have to take a large n limit. So you can actually look also at gauge theories with small number of flavors in SU2, SU3, SU4. And of course, the problem is, or like, the superior part of, like, what Umut told you about is you can use this construction phenomenology to understand condensed matter systems or quark plasma. This is only talking about, pure gauge theories. But okay, it has also the advantage I mentioned in one of my QFT lectures that you have gauge theories with no known Lagrangian description. And this method, the one I'm going to represent, actually allows you to construct gauge theories whose Lagrangian you cannot write down. And that's very, I will say, nice, because you have a handle on the theory. And the method is called geometric engineering. It's developed in mid-90s. So the basic idea is you start with type. Okay, so I hope, but I don't know. I don't remember whether Wolfgang mentioned this in his first lecture. But string theory comes in 5 different types, superstrings. So one of them is called the type 2 strings. Okay, and you have type 2A and type 2B. So you can start with the type 2A strings or M theory. So until this point, you probably never heard of about M theory. Wolfgang mentioned it too. So again, 1995 or 96, really constructed M theory, or argued the existence about M theory, because if string theory is the unique theory to describe the world, it should come only in one form, not in 5. So the uniqueness of the theory of everything is spoiled if you have 5 different theories. So that, but we can show this with M theory. Actually, despite if you go, and this is in 10 dimensions, he argued if you go to 11 dimensions, then you can actually combine everything under a single framework. And all these 5 different string theories are certain limits of this non-perturbative M theory. And actually, okay, on a side note, this I'm not going to talk about, we also have F theory. So the F theory is 12-dimensional. And this is as far as we go. We don't have a 13-dimensional theory for now. So the reason we have 12, okay, so M theory is used to unify, bring all these different string theories under the same framework. F theory is introduced because you have some dualities within type 2B string theory, which doesn't have a geometric explanation, and F theory provides a geometric explanation for those dualities in type 2B theory. Recently, over the 2 years ago, or about 2 years ago, F theory constructions became also important in phenomenological physics, or they have concrete predictions for LHC. So you probably hear always string theories and predictions. That's partially true, partially wrong, because in F theory there are F theory constructions where you have some LHC predictions where you can actually people compute cross sections and production rates. So But the F theory approach is a little bit different than the string theory approach, or different than from what I'm going to talk about, in the sense that it's going the opposite way. Usually what we do, we study that string theory and try to compactify this 10-dimensional theory of its space to get like a 4-dimensional theory. Here it is F theory constructions in the recent models. What they have done was something different. So they said, okay, we know standard model works. We know certain like hierarchies of standard model, mass splittings and stuff. So let's take all this data as an input and try to construct an F theory which can give these known properties. So unlike this is like construction where you start with like all possible and try to find a unique one, if you just go like bottom up, then you realize there are only 1 or 2 possible geometries where you can actually where you can write down the F theory. Which is good because the problem on this side is we have too many spaces on which we can compactify. But here the construction allows you to get 1 or 2 geometries. And then once you have the geometry, which gives you the known physics, and you can actually ask questions about unknown physics, and you can make predictions. And that's what they have done, like, extensively for 2 years. Okay, so here, I'm going to have the opposite idea. So I will say, okay, I have a 10-dimensional string theory, but we live in 4D. So this is our space-time. And we want to actually go somehow from 10-dimensional theory to 4D theory. So what do we do is compactification. Compactify. Okay. So we need to compactify on 6 dimensions. So as the name suggests, geometric engineering is the program that allows us to find what this 6-dimensional space is. So given a gauge theory, you want to get a specific 4D gauge theory. And then you ask yourself, okay, what is the 6-dimensional space? And geometric engineering gives a recipe of the constructed space, and I'm going to talk about that. So okay, let me just give you a simple example what you mean with compactification. The simplest example is R2. Imagine you have a 2-dimensional space. Okay. So one thing you can do is so let me also for the sake of argument, with a coordinate system on it. This is my y direction, this is my x direction, and I have this minus infinity here and plus infinity. So what I can do is I can identify minus y and minus infinity and plus infinity in the y direction. So I claim that each point here is exactly the same as here. What you get is something simple, you all know. A cylinder. Okay? So then you will have this direction. So once you have the cylinder, you can take the cylinder as you have a line, and on top of each point, each individual point, you have a circle. Okay. So I think it's clear, right? If I have a circle at each point, then I will get a cylinder. So then the idea is if I can then generically say I can compactify the plane, the 2-dimensional plane, on a circle to get a line. Okay. So I will do the same thing here. I will study the 10-dimensional theory, compactify that on a circle. So here, this circle in my geometric engineering description will be the 6-dimensional space. Okay, let me just internal space. Let me also introduce some jargon. And this line will be in my construction R3, the 4-dimensional space-time. So what happens? So I just study the 2-dimensional theory. I study the 2-dimensional theory, compactify on a one-dimensional space, and get a one-dimensional line. That's the same thing. So I start with 10-dimensional contact. If I want 6, I will left it like 4 dimensions. So, okay. So there are a number of questions you can ask. Right? So if you want to talk about the gauge theory, what are the possible questions? The first one is, of course, the gauge proof. Okay? This is the tricky part because if you have exceptional groups, you can have a Lagrangian description. But in this, as I'm going to represent, the gauge group is encoded in such a geometrical way that allows us to also go beyond what the field theories can go. So that's one thing, the gauge group. The other thing is, the other question you can ask is, let's say, supersymmetry. So how much supersymmetry you have? Okay, so you can have like n equals 1 or extended supersymmetry. What else do we have in gauge theories? We have method. And we have method in different representations. You can have method, let's say, adjoint representation. You can have method in the fundamental representation of the gauge group. So these are essential the 3 questions I want to address. So I want to start constructing my theory based on these 3 questions. So let me start with the gauge group. Okay. But before I go to the gauge group, let me introduce you a concept about what's called the orbifold singularity. Imagine I have the complex plane. I'm just going to give you this going to be an example. Imagine I have C, just a plane complex plane. So I can model C by what's called Z3. So Z3 is a group, and regarded as a group with 3 elements, 0, 1, 2. And it's just a small discrete group, which means geometrically, this quotient means, so I'm going to let's say start with a positive real line and identify this. Okay, so I'm going to identify the space with 120-degree angles. You, of course, guess, the 120 comes because of, I have 3 sectors and I just divide out 360 degrees by 3, so I get 3 angles. So what I'm doing is I'm identifying this line with this line on a point here with a point here. The same way also with this line. Okay. So if I identify this with the other one, essentially what I get is a cone. I think it's obvious, right? If I identify this with this, I'm just basically wrapping them to a cone. And there is an action here. There is a group action, which takes a point on this cone. And rotates. So if you imagine if we take a point here or any point, you can rotate this and then rotate different points. And I can choose any point on this cone, apply a rotation and go to another point, except the origin. If I rotate that origin, it will stay at the same point. It's not going to move anywhere. So when I mean a singularity, it's not something which blows up, but rather than a point, a fixed point under a group action. Here the group is the rotations, and the fixed point means the point is going to stay where it is if I apply this action. So for this one, I have this point, like a fixed point at the tip of the cone. So once you have a singularity, what you can do is you can actually replace this cone, replace this point with a sphere. So what I do is technically I put a smaller sphere here. And smooth out that singularity. Because the singularity is actually a tip. You can imagine that, in this case, it's a little more obvious. It's a tip. It's something which will hurt you if you poke in your hand like that. So you can replace this with a sphere and make it then you remove all the singular points, because here on the sphere there are no fixed points of rotation. If I rotate them, everything is going to be rotated. So this is called resolving a singularity. So this is the type of singularity. This is the definition of a singularity, of an orbital singularity. Okay. So what Collier did back in the day, he classified the singularities. He classified. So the classification turned out to be really close to the classification of Lie groups. So for different gauge groups, you can write very humor, as far as I remember, and it got the motivation from this, from the Himalaya mountains of the Himalaya, you have K1, K2, and then K3. So what he argued is if you can have if you have
understand how we transit from gauge theory to this stuff.
Okay.
In gauge theory, it means that we write down a phase and multiply it with a field.
Okay, fine. So here, what I'm going to try to give it. That's what I'm going to do. So I'm not going to look at the gauge transformations as local phase rotations as I explained in the QFT lectures, but I'm going to approach the problem from the point of view the gauge theory has gauge bosons or matter. So I just want to construct those gauge bosons. The singularities are classified with Cartan matrices. And the way it's done is, so imagine you have a singularity, and then you can resolve the singularity. So you will have a bunch of spheres. And imagine you have spheres like this. First one, the second one, the third one, blah 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 blah. The n minus first. Yes. And then I can construct what's called this intersection matrix. So what is an intersection matrix? So you just is given by the number at how many points they are touching each other. And conventionally, up to a sign, this is the self-intersection. A sphere with itself is considered to be 2. But there is a simple way to see this. If you have one sphere, because they are always going to cancel each other because of this orientation. And the number is going to be 2. It's like you have 2 spheres, it's northern and southern hemispheres, northern and south pole, and those are the 2 fixed intersections, and all other deformations are going to cancel each other in this picture. So it's going to be 1. The first one is not touching the third one, fourth one, fifth one, sixth one, and so all entries are going to be 0. Okay? So if I go to the second sphere is touching the first one at 1 point. Again, the self-intersection is 2. The first one is 0, third one is the second one is 1, it is up 2. Okay? So you get the matrix in this one. And it turns out these matrices are exactly the Cartan matrices you get when you classify the Lie groups. So that would be a chain of spheres, n-1 spheres. So then what I'm going to do is, if I want to describe an SUN theory, I'm going to pick a K3 surface, a K3 space, which has a singularity structure of like, in the show, K3 surfaces admit intersection matrices which correspond to exceptional groups. So you cannot write down Lagrangian, but we can write down the geometry 2. You will have A1. A1 will only have one sphere in a singularity, which is going to be embedded in like a big geometry, K3. So then, you have for SU2, you have like 3 gauge bosons. You have W plus minus. You have Z. How do I get them? DT branes. DT branes are 3-dimensional. So I grab like this 3-dimensional brane on the sphere. So I will left with one line. Right? If I start with 3-dimensional, compactify on or wrap on a 2-dimensional space, I will end up with an infinite line and end up with one form. And that's exactly giving rise to the Z. So with branes and like forms you have in type 2A string theory, you can get the gauge multiple. Okay? So let me go. So this answered the first question I asked, that the gauge. So I said, sure.
So you are getting the W bosons and Z bosons in a completely different way?
Yes. And one of them is like, you have like 3 forms integrated over like a size sphere to get like one form.
They have different geometrical interpretations.
You and the Z, we know that they are related to each other, they are equal.
Yeah. I mean,
Do you kind of fine tune that?
no, we don't. As far as I know, we don't have to. But I don't know. I mean, because I think like it's because somehow also the tools are sourcing like these 3 forms. So this is another like space issue. Okay. This is like a convention. This is a convention because I mean, usually we take this space. I just throw it as a bulk here, but usually we take a certain limit and we look at the tip. That's why I mean, we are just because I'm at the end of the resolution of those singularities. So you have a K3 with certain singularity structure. You resolve them. You just like blow those singularities with spheres. You resolve them. And then different type of like singularities will give you rise to, after resolution, different kind of intersection, which is a SUN theory. I need to choose a K3 surface which has that type of singularity structure. Okay. So I'm matching like the singularities after resolution, the intersection matrices to the gauge groups. Okay. So the second question is how much supersymmetry I have. So okay. Then you have 2 choices. You can compactify on a sphere or on a torus. If you compactify on any higher general surface with non-asymptotically free theory. So that's why since I want to like have a well engaged with asymptotic freedom, I'm going to restrict myself with this one and this one, the sphere or the torus. It turns out torus can support more supersymmetry because it's flat. Because supersymmetry support more, that's why you have a supersymmetry enhancement. And these theories are going to be n equals 4. And if you compactify on a sphere, it's going to be n equals 2. Okay. We are interested in n equals 2 because we know psi beta. For like reasons I can tell you the reasons. So you will end up like you will, as I said, you will look only the tip of this one because to get to decouple gravity and string theory effects, you have to take a large volume limit in which you actually ignore or you need to take like everything. So my geometry for let's say SU2 theory with n equals 2 supersymmetry turns out to be a sphere, and over each point of the sphere I have another sphere, which is actually embedded. There's a base. This is the base. This is what's called a hyper. It's a technical name. So each point on the base, you have another space, like base hyper on top of it. Okay. So we have 3 folds. Okay, so what happens if you have like, if you want to have like, you know, higher rank group, you have like different intersection matrices, and you again like, you know, fiber them or like, you know, put them over the sphere, and then it's going to, you know, the K3 surface corresponding to the singularity structure, and you can engineer them. Okay, so the third one, okay, the method is going to be more tricky, so let me skip a little bit. I mean, okay, I can tell you that the whole thing is a Calabi-Yau. Okay, so K3 is a Calabi-Yau two-fold.
Okay.
After you fiber this, like, you know, over the sphere, that's not a Calabi-Yau unless you introduce some additional structure, which is not very relevant. Then it's a Calabi-Yau three-fold. So this, and the idea is that the gauge group information is encoded in the fiber, and here in the base you have the supersymmetry essentially. The space you choose, like is a torus or like a sphere. So then this whole thing like is going to be 6-dimensional uniform. You can compact the constrictor on the type 2A theory on this. You get like, you know, the gauge theory you want. And as I said, you can even do that. You don't have to go to the large rank limit or large number of colors. One thing, okay, fundamental matter is, for example, for SU2 theory, you can actually have the base, and over each, like, you know, point, you can have this, like, you know, A3 with, like, you know, A1 singularity, except one point where you enhance the singularity to an A3. Look like as SU3, but you can decompose SU3 adjoint into SU2 multiplets, and this way you see under this decomposition you get fundamental. So the way you encode matter is like, you know, you just like, you know, enhance the fiber at one point and locate the base sphere at one point, and then you have like one fiber over this sphere, the other fiber over this sphere. When they collide at this intersection point of these base spheres, the singularity enhances, it opens up a new cycle, new sphere, and over that matter located on this extra sphere in the singularity above the intersection point of the base spheres, this matter is going to be charged under both the gauge groups, which is over one sphere as well as over the other sphere. So it's going to be charged on both. Okay. Good thing is the geometries, like this construction gives you what's called like, you know, a certain class of geometries for which we have like very sophisticated techniques, and we can, for a given gauge theory, we can plug this in and compute everything very easily. Like, you know, structures which Seiberg and Witten found in their own papers. So string theory provides a very geometric way of constructing gauge theories and tells us a lot of information about the dynamics of gauge theories and goes beyond what